Hi, I'm Emily,
And I'm Maggie.
and we're TCU students in Dr. Janesko's physical chemistry class. Today, we'll be investigating the mathematics behind a concept that every freshman chemistry student is familiar with, the chemical bond. To facilitate this discussion, we've decided to model the dihydrogen cation. This is the simplest possible molecule with only 2 protons and 1 electron, and since it only has these 3 moving pieces, it's known as a 3-body problem. Because it's so simple, it can actually be used to provide exact solutions to Schrodinger's equation, which is the essential equation for all of quantum mechanics. Note here on your screen the 2 protons sharing the single electron and the internuclear distance r between each of our protons. This variable becomes fundamental to our derivation later, so make sure to keep it in mind. So what was our whole goal with this derivation? Well, we sought to derive a quantum mechanical model for the energy of our dihydrogen cation as a function of this internuclear distance r, so that eventually we could compute a bond dissociation curve and learn some interesting things about our molecule and about molecules in general.
To do this derivation, we will use the postulates of quantum mechanics, the principles of physics and chemistry, and then some calculus and some algebra. The bond dissociation curve is a graph of total energy of the molecule versus its internuclear distance. So, how can the total energy of this system be described? We're going to use postulate 2 of quantum mechanics. Postulate 2 of quantum mechanics states that every measurable value has an associated mathematical operator. For the total energy, the operator is the Hamiltonian. The Hamiltonian depends on the system, and because our system can be described with electromagnetic forces, which are approximated as the Coulomb force, and because the motion of the protons is neglected because they are so large when compared to the electron, this is the Hamiltonian for the dihydrogen cation. Each term in it stands for something that affects its total energy. The first term is going to account for the kinetic energy of the electron. The second term is going to account for the attraction of the electron to the first proton. The third term is going to account for the attraction of the electron to the second proton. The fourth term is going to account for the proton-proton repulsion. And then R1 and R2 are the distances between the electron in each respective nucleus. To further describe the energy of this system, we're going to return to the postulates, and this time postulate number 3. Postulate 3 states that an individual measurement of an operator will only return an eigenvalue of that operator. As can be seen in this general expression, when the Hamiltonian acts on a wave function, it returns the eigenvalue of the Hamiltonian, which is the energy. Before we continue describing the energy, how can we describe the system itself? That brings us to the first part of postulate 1, 1a. This states that every system can be described by a wave function. For the dihydrogen cation, we are going to treat the molecular orbitals as hybrids of each hydrogen atom's 1s atomic orbital. This is the 1s wave function of the hydrogen atom, where 1, 0, 0 are the quantum numbers n, l, and m of the hydrogen in this 1s state. We call the wave function for the first hydrogen atom psi1, and the wave function for the second hydrogen atom psi2. So, conceptually, what is happening in this system? This is a GIF of the spherical 1s atomic orbitals of hydrogen coming together to form the bonding molecular orbital on the top and the antibonding molecular orbital on the bottom. We need to model this mathematically. How are we going to do this? We do this by trying a linear combination of the atomic orbitals. So we're going to add the 2 wave functions to make one new wave function, and then we're going to subtract them to get another new wave function. These wave functions, psi plus and psi minus, signify the bonding and antibonding molecular orbital wave functions for our molecule. We can then get a generalized wave function, psi plus minus, which makes further mathematics more simple. We have this new variable pop up, c plus minus. What is it? It is going to be the normalization constant. And this is going to bring us to the second part of postulate 1. 1b. This states that a wave function must be normalizable. This means that, in our case, the electron must be somewhere in the universe, so the probability of that happening is 1. Though this term won't show up in the final energy expression, it is still integral to evaluate it. Representing this mathematically, the integral over all space of the wave function times its complex conjugate must be 1. This is a real system with no imaginary term, therefore a wave function and its complex conjugate are equal to each other. This is the equation for our system so far, expanded out and written in Dirac notation. This is pretty complicated, but like a lot of things in quantum mechanics, this can be simplified. So the first and second term are going to be the integral over all space of a wave function times its complex conjugate. So these are both going to be 1. The third and fourth term are a little bit more complicated, so we are going to name these S and S star. The S star is because the fourth term is the complex conjugate of the third term. We're going to further describe these as the overlap integral. And so remember, S and S star are equal to each other because these are real systems. So after simplifying this, we get these expressions that involve C plus minus, the normalization constant, and the overlap integral. What is an overlap integral? You can see in this probability distribution, the top graph shows a region of space where the two wave functions overlap and there is a non-zero probability of finding the electron there. This is the bonding molecular orbital. There's no such overlap and thus no probability of finding the electron in the middle region in the bottom graph, and this is the antibonding molecular orbital. So we now need to evaluate S. And we get this integral after we expand out our Dirac notation. This integral can be simplified to get a more solvable one, which we evaluated and obtained this expression, which is only dependent on the internuclear distance r. Let's get back to how we can describe the energy of this system. This is going to bring us to our fourth postulate. Postulate 4 states that many measurements of an operator or an observable is the expectation value for that operator on that system and is the average value of many measurements. This expectation value of the Hamiltonian is the energy, and that is shown in this general formula. This is the expectation value for our system, psi plus minus. We're going to then expand out the Dirac notation to get this equation that's made up of 4 integral terms. We're going to name these 4 integral terms. The first one's going to be H11, the second is H22, the third is H12, and the fourth is H21. These are pretty complicated, but as said earlier, these can usually be simplified. So H11 and H22 are going to be equal to each other, and then H12 and H21 are going to be equal to each other. After simplifying this expression, we get this. It's only dependent on the overlap integral and then H11 and H12. Now we are going to evaluate H11. To do this, we expand out the Dirac notation to get this expression. The first term is going to simply go to the energy of the single hydrogen atom. This is because when you act on psi1 with this operator, it's going to return the energy of the hydrogen atom, and then we're left with the integral over all space of psi1 times its complex conjugate, which again, because of normalization, is 1. The second term is going to be the proton-proton repulsion of the system, which is also multiplied by 1, because again, this is the integral over all space of psi1 times its complex conjugate. We're left with one last integral to evaluate. This is the integral after we expand out the Dirac notation, and then after evaluation, we get this expression, which is dependent only on the internuclear distance r. So now let's move on to H12. We're going to again expand out this Dirac notation to get this expression. Because of the same reason as H11, the first term is going to go to the energy of a single hydrogen atom, but this time it's multiplied by the integral over all space of psi1 times psi2. This is going to be the overlap integral S. The second term is going to be the proton-proton repulsion of the system, which is also multiplied by S, for the same reason as the first term. So we are left with one integral to evaluate. After expanding out the Dirac notation, we get this expression for H12, which is further evaluated to get this final expression. We're now going to substitute these evaluated integrals into the expression for E plus minus. It's pretty complicated, but after using a few algebraic substitutions, it can be simplified to get this expression, which is the general energy formula for the antibonding and bonding molecular orbitals of our dihydrogen cation. These can further be specified to the bonding orbital seen here, and then the antibonding orbital as seen here. This equation can then be used to determine the energy of the dihydrogen cation as a function of the internuclear distance, and thus the bond association curve can be computed.
So now that we have this equation to find the molecule's total energy, what can we actually do with it? Well, you can enter it like we did into Excel and plot it as a function of the internuclear distance r. When you do that, you generate a graph called the bond association curve for your molecule. The bond association curve tells us several useful things. First, let's look at how the total energy depends on r. As r goes to 0, the graph approaches infinity, which means that the energy of the molecule continues to increase as the distance between the atoms decreases. This is due to the proton-proton repulsion that Maggie mentioned earlier, because as the two positive charges get closer and closer together, the repulsion increases the molecule's total energy. As r goes in the other direction towards infinity, the atoms move further apart and the energy of the molecule approaches the energy of the lone hydrogen atom. This energy is known as the dissociation energy. Here, the energy of the molecule when its atoms are infinitely far apart is the same as if the atoms were not interacting at all. So next, let's look at the minimum point on our bond association curve. Here, it's marked RCD. At this point, the energy is at its lowest, so the molecule is at its most stable. But the difference between this minimum energy and the bond association energy is also significant. It's known as the binding energy. This energy difference is the amount of energy that you would have to apply to break the dihydrogen cation bond. The R value, where the minimum energy occurs, is also significant because it's the equilibrium bond length of our molecule. Recall that even though our protons were assumed to be stationary for this derivation, in real life they're moving back and forth as if they were on a spring. So at this equilibrium internuclear distance, the repulsive force of the protons is overcome by the attractive force of the protons to the single electron. So knowing all that, let's examine the bond association curve produced by this derivation. You can see here on the left the graph of the bonding, antibonding, and lone hydrogen atom energies as a function of R. Note that the bonding orbital crosses below the energy of the lone hydrogen atom at around 2 and reaches a minimum a little below negative 0.5 Hartree. The antibonding orbital in gray, however, never passes below the lone hydrogen atom energy, implying that it's less stable than the hydrogen atom by itself for every internuclear distance r. On the right, you'll see another researcher's bond association curve. The dashed line represents the experimentally determined curve, and the solid line represents their computed curve. So let's see how our results compare to the experimental values. Here, the negative 15.71 electron volts is very close to the negative 16.4 electron volts of their experimental minimum energy. The binding energy is also relatively similar, 2.1 versus 2.8 electron volts, and the bond length of 1.14 angstroms compared to the experimental value of 1.06 angstroms is only about a 7.5% error. So now that we've used the wave functions to find the molecule's total energy, let's use them to compute probability distributions. So the wave functions from earlier were input into the formula for the probability distribution, which is just the wave function squared times a small volume. In doing that, you plug the equations into Mathematica and generate the probability distribution shown here. The one on the left is the bonding orbital, and the one on the right is the antibonding orbital. The key difference between the two is the area between the two peaks, where the peaks are the centers of our atoms, the protons. Notice that on the bonding orbital, the graph reaches a height of about 0.05 between the two peaks, which means that the electron has about a 5% probability of being here. This fits with our idea of a chemical bond. The electron is shared by each proton, and the electron densities overlap to create a bond. In the antibonding orbital, however, there's no electron density between the peaks, implying that the electron has a 0% probability of being there. This empty space is called a node and occurs because we subtracted our two wave functions earlier. So let's put all of this together. First, we found the wave functions for the hydrogen atomic orbitals and added and subtracted those to generate bonding and antibonding molecular orbitals, respectively. Then we took those molecular orbital wave functions and applied the Hamiltonian to generate bond association curves so that we could find the bonding energy and bond length of our molecule. We also used the molecular orbitals to generate probability distributions by inputting them into the probability equation and plotting them on Mathematica. These probability distributions showed us which spaces were most likely to find the lone electron. So there you have it. We've described how quantum mechanical wave functions can be utilized to predict atomic properties. Now, in more complicated molecules, you need additional approximations and calculations, but it all comes back to the same framework outlined here.
We hope you like the dihydrogen cation as much as we do.
Be sure to follow @Janesko Research on Twitter.
Thanks
Thanks for watching.